Okay, suppose we have one particular problem. We have one particular, we have a block, basically, on the left, block M. And then on the right, we have a spring system. Okay, okay. What happened is this particular block is going to slide. Okay, it start from rest, then it will slide down, slide down, and finally hit this spring. Okay, hit this spring, and therefore the spring will compress due to the uh, impact or due to the force from this particular block M. Okay, and let's say this is our point 1 and this is our point 2. So now um, note that on this particular surface M, the inclined surface, you have mu k1. Okay, and on this horizontal or flat surface, you have mu k2. Okay, so on this surface, the roughness is not the same as this surface. Okay, the friction will be different. So what we can say is mu k1 is not equal to mu k2. Okay, now for this particular problem, we want to know how much the spring is being compressed due to the force from M. Okay, and we need to also include the friction on both surface. Okay, we look on the inclined surface. So to draw the free body diagram for this one, what we have is we have a block M incline, and as this move downwards, there will be a friction force. Okay, friction force 1, I would say. Okay, then going down here, you have W, which is mg, of course, and making a theta. This one is inclined with a certain angle theta, and here you have the theta as well, and you have the normal force, which is I put it as N1. Okay, on the other hand, on this at point 2 for block M, what we have is of course the weight here, which is mg, and friction at point 2. Okay, this one is 1, this one is 2, and you will have a normal force 2, and the force exert on this spring system. I put a F spring, Fs. Okay, okay, now from the energy principle, we know that the energy E1 must equal to E2, which what we have in this particular problem. Okay, remember this is what we want to determine. Okay, E1 is equal to E2. What we have is a K kinetic energy at point 1 plus the potential energy at point 2 plus any sort of other losses, I would say, then equal to kinetic energy at point 2 plus potential energy at point 2. Okay, this is the things that we have so far. Okay, let's look one by one. Uh, Kinetic energy 1, okay, because you start from rest, so therefore it is equal to 0. Then how about the potential energy 2? Okay, initially this block M is located at the height of h, okay, at a height of h, so becomes simply mgh. Yeah, then uh, for the forces due to the friction, what we have is we have W1 plus W2, because we have this component here and also this one. Okay, it is negative because of okay, I forgot to put this. Okay, the because it is on the opposite direction, so W1 is equal to um, minus F1 time S1. What is S1? S1 is the distance from the initial position until the end here. Okay, we are looking into this point from here to here. Then from here to all the way to when it is stopped. Okay, minus F2 S2. Okay, this one is S2 and this one is S1. Okay, now what is FF1? Okay, FF1 is mu K1 time the N1 times N1 S1 minus this one is mu K2 and 2 S2. Okay. Okay. What is N1? Okay. This one we can further expand it. Minus mu K1. N1 is see this one from this particular figure. N1 is equal to mg cos theta. Okay. So we have mg cos theta, and don't forget to multiply by s1. Okay, for this down here, we have mu k2, okay, mu k2 times uh, I think I made a mistake here. Actually, n is mu k1, sorry, mu k2 mg. Okay, on this one, n1 is equal to this multiplied by mu k1. Okay, so just ignore this part. Okay, ignore this part. Okay, mu k1 mg cosine theta s1. Okay, and then mu k2 times mg then time the distance. Okay, the last part is we have KE2, and we know that when it is reach compressed this particular spring, it just stay there, no motion involved. So KE2 is equal to 0. Okay. How about the potential energy on this spring? Because the spring is being compressed, so the compression is there, and therefore you will have a potential energy. Sorry, not M, but kx square. Okay. Now you can supply all this information, put it in this formula. So what we have is KE1 is equal to 0, right? This one is also equal to 0. So 0 plus PE, sorry, this one should be PE1. Okay, I made a small mistake there. Okay, PE1. Okay, this one is PE1. Okay, is equal to mgh. Then you have this component here, and this part is actually this, right? Which is equal to mu k1. I put a small k, I think that's better because may, okay, that's better. Mg cosine theta times S1 minus mu K2 mg, then multiply by S2. Okay, and that is equal to Ke2 is equal to 0. And how about this part? That is half kx squared. Okay. Okay, now we can rearrange this equation. Okay. Then finally, when you do the math, what you get is x is equal to square root of, okay, mgh minus mu k1 mg cosine theta times s1 minus mu k2 mg times s2 divided by k. Okay, it is the answer. That's all.